Okay. Law of inertia, part 2. So in part 1, we saw that Newton's law of inertia, which is also known as Newton's first law of motion, says that an object moves with constant uniform motion until acted on by an unbalanced force. So if all the forces are balanced, like in this example of a bowling ball rolling on the floor, the weight of the bowling ball, that downward force of gravity, being balanced by the upward support of the floor. So in this case, there's no unbalanced force, and so we have constant uniform motion. The speed of the bowling ball is constant. It moves in a straight line. This is a bit of an approximation because there's going to be a little bit of friction that's going to slow the motion, but pretty much Newton's law of inertia applies here. Now, Newton's law of inertia also says that an object at rest, and by at rest we mean it's not moving, not that it's relaxed or taking vacation, but an object that's not moving remains at rest until acted on by an unbalanced force. So, talking about the bowling ball again, if the bowling ball is just sitting there on the floor, stationary, then it will remain stationary until some unbalanced force comes along, like someone kicks it or something. Now, if you think about it, this is really just a special case of what we saw in part 1, because this is just uniform motion when the speed happens to be 0. But it's important enough that it's worth pointing out as a special case that occurs very often. Now, the classic example of the law of inertia for an object at rest remaining at rest is the tablecloth pull. So in this case, we have a vase of flowers, and if we have a tablecloth that is pulled out from underneath the vase quickly, then there's only a very small force that is acting, and then the inertia of the vase keeps it in place. Let's look at a quick video of that. Ta-da! Here's another similar example, only instead of a vase we have shopping carts, and instead of a tablecloth we have a truck that the shopping carts are sitting on top of. So these shopping carts have been loaded in the back of this truck, and now the truck leaves the store, and because of the inertia of the shopping carts, they stay in place. In particular, the row on the right-hand side, you see that the shopping carts stay in their original position as the truck moves out from under them. Now, a more simple, common example of this would be if you're riding on the bus, and let's say that the bus is sitting at a stoplight, so it's not moving, but then it suddenly starts moving quickly, so it accelerates. Well, you will remain stationary at rest until there's a force acting on you. So in this case, it seems as if you are thrown backwards as the bus moves out from underneath you. Now, you have to realize that it only seems as if you are thrown backwards because if you are an observer moving with the bus, so let's say someone sitting in the bus watching you standing in the aisle, so that person will be moving forward with the bus, and so from their point of view it seems as if you're moving backwards because they're moving forwards. On the other hand, if we look at this picture on the right, if there's someone standing outside the bus, say on the street, and they're looking in the window, and they see you falling, they actually see you falling in place as the bus moves out from under you. Let's do a little experiment of that. So if we go frame by frame, starting with the initial position of the doll, we see that the doll actually stays in the same spot, at least the center of the doll stays in the same spot. It rotates around that spot as the car moves out from underneath. So in this case, of course, it falls out the back of the car, but is actually, from the point of view of the camera, remaining stationary. So in summary, the law of inertia states that an object at rest, which means not moving, remains at rest until acted on by an unbalanced force. The classic example of this is pulling a tablecloth out from under a vase. The inertia of the vase keeps it in place as long as the force on the vase when you pull the tablecloth out is small. So you want something which is fairly slippery, and do it quickly so that there's very little time during which the small force would be acting. And then finally, the last example points out that when you have a situation where the camera is accelerating away from a stationary character, then it seems as if the character is being thrown backwards, just like we saw in that example with the bus. There is no force throwing the character backwards. The character is actually remaining in place, and the camera is accelerating away from the character. And so from the point of view of the moving camera, it seems as if it's being thrown backwards. But if we have a stationary camera, like someone standing outside the bus, then the character is remaining in place from that point of view. Now, if this reminds you a bit of drag as is used in animation, so when, say, a character is moving and the hair seems to drag behind, or the clothes drag behind, well, indeed, this is also an example of inertia, and it's important enough that we'll cover it in a separate tutorial. So I'll see you then.